All right, and we're back. Let's take a look at some things. So we've gotten into the concept that we've got schematic representations of the piston moving inside of a schematic representation of the cylinder. There's the schematic representation of the cylinder, and there's the schematic representation of the piston. And we also have created the previous drawing where we laid in these transceivers. So there's a cylinder wall transceiver D is sitting on what we have listed here as cylinder wall position D. So what I have done in the next set of drawings is taken all of this cylinder wall transceiver information out of the drawing to make it easier to show what I'm trying to show. But this position in the cylinder wall of E actually will have sitting in that place called E a cylinder wall transceiver called E. So if we go back to this other view, there is a spot here called E, and in your mind you need to imagine that there's a cylinder wall transceiver sitting here. I kind of wanted to look through and see inside there and see these transceivers, which gets very hard to do if there's a look through here and see these piston transceivers. It's hard to look through there and see the piston transceivers if there's cylinder wall transceivers in place, and so I just took them out, but they're there. Okay, so the other thing that we're remembering is that this piston, so here's the piston, this piston can move inside of this cylinder, and as you can see by this demonstration I'm doing here, when you have a piston that's moving inside the cylinder, then the radio frequency output of the transceivers of the piston, that radio frequency output will be picked up, broadcast into, will be seen by different transceivers of the cylinder wall. And we're going to work through some math issues associated with that, to let you see what the issues are and how there's a possibility that we can use strategic understanding of power levels and relationships to enhance the accuracy of our knowledge of the positioning of the piston. And one thing that needs to be mentioned is that the current dimensions on these drawings is 100 millimeters by 300 millimeters. And the reason that these drawings are made at that size is that if you bring these drawings down to sizes that are exactly equal to what's going on, SketchUp does not like drawings in those small of a size, and it winds up not being able to draw it. And so everything has been increased in size. But in the real world, it has been my discovery with these transceivers in the real world that it's a little bit difficult to get their for a number of reasons, beginning or including that they keep changing how they're making them, and there is always a pressure to make these transceivers smaller and smaller, more and more efficient, using less and less power. So every time you carefully investigate how big they are, it changes. In addition, there is an issue associated with the size of these transceivers, which is related to the antenna, because the actual use for these transceivers is to send data out over distances like 3 to 4 feet up to 20 feet, or maybe a room of 30 feet, and perhaps through a wall, or at least around obstacles in the room. And so the antenna becomes important. Remembering that all we're doing with these transceivers is sending radio frequency information through the wall of the piston, through the wall of the cylinder, and sending that information through a ceramic material transparent to microwaves. So we may not need anything remotely close to the type of antenna capability that is typically built into these. It's been my finding so far, at least now, that this distance on these transceivers is about 2 millimeters. This distance is about 6 millimeters. The thickness is somewhere between 1 and 3 millimeters.